So here we have a star. It's like Betelgeuse or something bigger. We're going to zoom in, and we're going to watch it collapse. So the first thing I want you to see is that this is the gas near the black hole that's just formed. The black hole formed as the star collapsed in on itself. And as it collapses, rather than, say, making an explosion immediately, like some stars do, it just keeps on sucking up the gas because it's a black hole, right? And as it does this, it sort of forms a disk around the black hole. And once it forms that disk, it just keeps on sucking in. Now here's the cool thing. Once you form a disk around a black hole, the black hole can't eat all of it. It actually is able to squirt out a jet, kind of like taking a tube of toothpaste and squeezing it as hard as you can. That's what happens near a black hole, and that's what you'll see in the rest of the movie. So here we see the black hole. We form the jet. We're looking at the surface of the star. Eventually, the jet penetrates the star, and we see the jet. Now, if the jet was pointed at us, they're rotating it. That's what we see as the gamma ray burst. So imagine a star. It collapses, forms a black hole. There's sort of a disk of material around the black hole. It squeezes out a jet, which punches through the star. And finally, if that jet is pointed at us, it's just like a laser beam. Don't worry, I won't blind you. It will actually be very, very bright. There's other ways of creating this kind of gamma ray burst. You can collide two neutron stars, and you can ask about showing the movie after the talk. Or you can collide neutron stars and black holes. And it turns out that black holes colliding with black holes does not produce a gamma ray burst. They're too clean. You need to have something like some plasma, some gas around to create a gamma ray burst. Oops, something bad happened. Okay, my screen looks funny. Okay, so one interesting thing about gamma ray bursts is that it's possible for them to affect Earth. Now this looks kind of scary, right? Well, it actually isn't that bad. But what's the idea? It turns out that there's about one gamma ray burst every 100 billion to 1 billion years in our own galaxy. And it turns out that life has been on Earth for about 3.5 or more billion years. So that means that there's a possible chance that there's a gamma ray burst that since we've been around, and it might have affected us. Now, it turns out that there's even a star that is about 8,000 light years away in our own galaxy that seems pointed at us. When I say pointed, I mean that there's a disk that could form and a jet that could form that would actually beam us toward us. Well, it's not this bad. It turns out that it's more like this, so don't be scared. The Earth will survive, but there's some problems, some major problems. If the gamma ray burst, like that star that was about 6,000 light years away or so, actually went off and was pointed right at us, it turns out that it would be equivalent to detonating 100,000 50 megaton nuclear bombs right next to us. Ooh, that can't be bad. That can't be good, I mean. So it turns out that's equivalent to like detonating all of Earth's nuclear bombs 100 times over. That's pretty bad too. And on the surface that's actually facing the gamma ray burst, only that surface, the other side survives, it turns out that you get 10 times the lethal dose of ionizing radiation. Oh, that's bad. And finally, even if you survived on the other side of the planet, it turns out that the gamma ray bursts and the gamma rays would burn nitrogen, create nitric oxide, which erodes the ozone layer. And for that particular event, if it went off, it turns out it would take about 5 years for the ozone to recover. This is bad because you would have UV finally reaching us in intense, very intense luminosity, and it would eventually cause the loss of the food chain. And it's maybe related to some mass extinctions. But the likely story here is that probably this is not quite right. We are still in the very beginning of doing the calculation. Not me personally. So now we're back at the visible universe. I'm going to zoom in on the Virgo cluster here. Now I've zoomed in. Now we're still in the center. We have here the Virgo cluster. And on the scale of 2 billion light years, what's interesting here is that these are collections of superclusters. A supercluster is simply a large collection of galaxies. And here we have our own. Well, it turns out that even on these scales, there are sometimes events, such as a supernova. This is also a star dying, but it's not as violent as a gamma ray burst. So let's look at that event. So a supernova is when a massive star dies, but it's not so massive. It's not 20 or 30 or 100 solar masses. It's only about 10 solar masses. And it most of the time will create one of those neutron stars, not a black hole. Only rarely does it create a black hole. There's about 2 per century on our own galaxy. And we're looking for them constantly. And about 10 per second in the visible universe. So it's quite a frequent event. So here we have, say, Betelgeuse. It's about 1 light hour in size. And I'm going to show you a little movie here, let's say this one, which shows the formation of the supernova event. So what we're going to do is we're going to zoom in again into the central region of the star. And once we're in the actual core region, what you'll see is the formation of layers. And that's because we've gone through a process where we've already burned all the hydrogen. Now we're burning helium. And the purple now is we're burning carbon, and then we'll go to oxygen. And finally, we'll reach iron. You can't burn iron. That's what causes collapse. And the collapse happens, you form your neutron star, and that creates an explosion because it's a very violent reaction. And finally, in the end, what you have is a neutron star that can be rapidly rotating. And if you know what magnetic fields are, they actually have very strong magnetic fields, and they spin around, and like a lighthouse, they actually will show us their pulses. And that's what you saw in the very end. It was a pulsing or pulsar neutron star. OK, so let's review where we are now so you get an idea. Take a breath. So it turns out that supernovae occur when a massive star dies. And it can be 30+ solar masses, or it could be even when you want to create a black hole. If you want to create a neutron star, you can have something like 10 solar masses. But black holes really require these big monsters. Gamma ray bursts occur when you have a so-called hypernova, which is an extremely powerful type of supernova. Or when you collide two neutron stars, they actually merge together and create a gamma ray burst. And they all create the same kind of event. They have a black hole that forms, a disk around it, and a jet squirts out. And the gamma ray burst is when we see the jet down the barrel of the gun. And we also have neutron star black hole collisions. This creates a gamma ray burst. And as I mentioned, black hole and black holes are too pure when they collide to create gamma rays. OK, so we're back at the group of superclusters. Now we're going to zoom in to this little region here and go actually to our own supercluster called Virgo. This is a poor quality figure, but it shows the supercluster. These are all little individual galaxies that we have in our supercluster. There's M87, which I'll talk about in a second. And we're here in the so-called local group, where Milky Way is, our galaxy. This is about 75 million light years across. What's interesting about M87, as I mentioned, we'll look at it, it kind of looks boring here, right? It looks kind of just like a fuzzy ball, about 25,000 light years in size. Well, it turns out that it's about 1/4 of the size of the Milky Way galaxy that I'll look at later, but 10 times more massive. This has interesting properties. It causes it to also produce a jet. There's so much mass, and there's such a huge black hole there, that it has one of those disks, and it squirts out one of those jets. Well, let's look at a little movie of that. So inside M87, we're going to zoom into the inside of M87 here. It has a 3 billion solar mass black hole, like I mentioned earlier. And I just want to comment here, just to give you this idea. Nearly every galaxy has one of these big black holes in them. Maybe it's not this big, but it's pretty big. So here we've just zoomed in. We have the disk that we call the accretion disk. It's swirling around. And as we get close enough, eventually the gas is getting hotter because it's hitting itself. It's kind of like friction. It's like you rubbing yourself. And eventually, finally, once you get close to the black hole, the friction is so high, the heating is so intense that it can emit in very bright light. And finally, when you get very close to the black hole just can't take it. It's too much stuff. So it spits some of it back out. And it spits it out in a jet. So the idea here is that black holes are surrounded typically by this kind of disk, and some of them make these jets. Here's a sort of more schematic of a cartoon. It turns out that here's the black hole. You have a disk around it. It's like a cutaway. Now, the key thing I want to show you here is that the disk and all of this matter, all this stuff that's getting hot, it's a special kind of matter. It's something we call plasma. And you've probably all touched plasma balls before, right? You put your fingers and play it around and, I don't know, other things. And now, this is what all this gas is made of. It's all a plasma. And this is what makes it so intense. And it became a plasma because it got so close to the black hole that it became very hot. Okay, so now we're back on our supercluster. This is our own Virgo supercluster. Now we're going to zoom in to the Milky Way, our own galaxy. Oh, I'm sorry, the local group. So now we're in the local group area. So here it's kind of a complicated picture. There are all these little galaxies that are numbered. You can see them sort of strewn around. These are actually to scale on size. Now, if you look at these kind of things, these are actually where are numbered, and they kind of give you an idea of what some of these galaxies look like. Here's the main point. This is our galaxy. It's one of the biggest ones. And there's another fun one that's called Andromeda. Andromeda, despite its being smaller, this number 21 here, it actually has a black hole in it that's 10 times bigger than our own black hole. And it also interesting is that eventually these two galaxies are going to merge and collide. This will actually happen in about 2 to 3 billion years. This is before our sun will sort of die. It'll happen long before that. So that's kind of interesting. So let's watch a simulation of these two galaxies merging. Do you think that we'll survive it? Do you think it'll be okay? Well, here's our galaxy. Oh, looks like we are okay. Not much damage. Here's our Milky Way. We kind of survived, right? Not to worry. Oh, well, wait a little longer. Eventually, Andromeda passes through us and completely rips us apart. So that can't be good. Eventually, this entire merged object will become kind of like M87. It will kind of become an elliptical galaxy. Sorry. It will have been that spiral. Both of them were spirals. It merges. They become elliptical. And this is how you make ellipticals. You merge other galaxies. Just to mention, the distance between us is about 2.5 million light years. And it's going to take about 3 billion years for all this to happen. So now we've zoomed into our own galaxy. We are here at the edge where the sun is. Our galaxy is about 100,000 light years across. And what's interesting about our galaxy is that it has its own set of black holes. These are smaller. There's one at the middle we'll talk about later. There's also these kind of events, these jets that are produced by black holes that are sort of littered throughout our galaxy. So these are called black hole X-ray binaries. They're called binaries because they always involve, like I showed before, the black hole and some kind of companion star. So they come in pairs. The companion star is stripped by the black hole. The gas is stripped off the star. It forms a disk. And just like you, when you always have a disk around a black hole, it's very likely to produce a jet as it gets too close to the black hole. The disk is so hot that it emits an X-rays. This is why we call them X-ray binaries. So you see the whole name now. Black hole because it has a black hole, X-ray because it's bright in X-rays, and binaries because there's a companion star that is feeding the black hole. There's about 100 of these in our own galaxy. And right now we think we have very good observations about 25. I'll show a little movie of this. So here we have our X-ray binary. There's a companion star, and this is the disk. And as you get close to the black hole, it can kind of be swirling around in a very complicated way. And this has to do with sort of called precession effects and relativity. But overall, it's just roughly the same picture. There's always a black hole. There's a source of mass. It forms a disk, and eventually can produce a jet. OK, so now we're going to go to the galactic center. We're back at our galaxy. Now we're going to zoom into the center of the galaxy. Here we are, near the center of our galaxy. What's special about the center of our galaxy is it has a large collection of stars very close to the black hole there, actually, that we figured out eventually was a black hole. The black hole will end up being here. This whole thing is only light days, 10 light days across. It's very small now. And when we watch these stars, we'll actually notice that they behave funny. They kind of move quite quickly near this little cross. The reason why they're behaving so fast, or moving so fast, is because there's a black hole there. And how do you figure that out? What you do is you just use standard Kepler's laws of motion. You know when a star orbits that it will trace out a path according to Kepler's laws. And through Kepler's laws, you can figure out what the other mass was. That cross is where the other mass is. And it's a mass of 4 million solar masses. So it's 4 million times bigger than our own sun in this little space. And the stars are whizzing around it. Now it turns out what's neat about the galaxy's center, it's probably the most modern evidence that black holes really have to exist. People have really tried really hard. Theorists are very creative people. They can come up with the craziest things. And it turns out that all those crazy things just don't work. Black holes are always better. And just so you know, the black hole is called Sagittarius A star. If you ever hear that again, Sagittarius A star. So let's review. Black holes grow by sucking in and accreting gas. This can happen during, say, a gamma ray burst. Black hole is born, and it can actually continue to grow by sucking in the star's envelope. You can be at the center of the galaxy and suck in gas from the center of that galaxy. Or in an X-ray binary, you can grab matter from your companion star in the binary relationship. You can also grow black holes by merging the galaxies together, because each galaxy has one of those massive black holes. And when they merge, it turns out that you're very likely to have those black holes merge too. And we figure out the mass of the black hole by using Kepler's laws. It's very simple. Black holes, when you're far away from them, are no different than any other kind of object. They have mass, and you can use that to measure the mass. OK, so I'm going to go through, now that we have sort of our repertoire of objects, I'm going to compare them and compare their power output to things we are more familiar with. Now, one of the things you can do is you can say, what is power? And you can measure it. Well, power is just the energy divided by time. If you imagine an event occurs and it has a certain amount of energy output, you divide by the amount of time it took, that's power. Now, just to give you a reference point, one light bulb is, of course, 100 watts or so. And each US citizen uses an electrical power of about 10 to the 4 watts. Now, just for fun, you remember the Back to the Future movie? How many people know about that? How many people can name the professor or whatever that was in that movie? Emmett Brown, yeah, Doc Brown, right? So he was a little bit insane at one point when he was trying to figure out how to get back to the future. And he needed his flux capacitor to have 1.21 gigawatts. Well, you can see that that's a kind of a lot of, it's actually about 1 billion watts. It's actually a lot of power. But look how far we have to go. So it's actually not too much power. Now, what's interesting is you can start comparing some of these things to other things we know of. I'll skip a few things. I'll go down to one very interesting one. It turns out that the largest nuclear weapon ever detonated was a fusion bomb, device created by the Russians. It's called the Tsar Bomba. And it was 10 to the 24 watts. This is many, many tens multiplied by each other, larger than anything we normally experience. This is a very violent event. Now, our sun, as a reference point, puts out about 10 to the 27 watts. It's just a little bit bigger than the Tsar Bomba in power. And if you want to get sort of a feel for what is all these watts mean, you can imagine, well, 10 to the 17 watts from the sun hits the Earth. So when you step outside and you feel the sun, imagine that over the entire surface of the Earth, that's 10 to the 17 watts. Now, some of these other black holes also create a large amount of power. There are those X-ray binaries, create about 10 to the 32 watts, which is about almost a billion Tsar Bombas. There's a lot of power. Our entire galaxy, or M87, creates about 10 to 37 watts. We're really getting up in their numbers. The numbers sort of become meaningless at this point. You just kind of keep track of the power index. And gamma ray bursts are extremely powerful. They're about 10 to the 45 watts. These are one of the most powerful events in the universe. Compare that to all the stars in the visible universe. There are about 10 to the 11 galaxies in the visible universe, or 10 to the 23 stars. Turns out that that's about 10 to the 48 watts. That's just a little bit different than a gamma ray burst. That means when a gamma ray burst goes off, it's about 1% as powerful as all the stars in the entire universe. It's an extremely powerful event. Do you have the time? OK. So now let's talk about gravity. And we'll talk about black holes in detail, very close to the black hole. Gravity is actually really simple. Might be confusing in some levels, but in other levels, it's actually really simple. Gravity is just the curving of space and time. And it's caused by any source of energy, be it your mass, your motion. Even when you wiggle your hand back and forth, you're creating a little bit extra gravity. Now, how can you understand how this happens? Well, imagine taking a star, and let's make it smaller and smaller by holding its mass constant. So it becomes denser and denser. It turns out that the way you can represent this curvature is by like a rubber sheet. And eventually, this mass puts a bigger and bigger dent in the rubber sheet. And it becomes deeper and deeper. That's all gravity is. Now, how do we understand Einstein's relativity? That's actually also simple. Gravity causes attraction. We know that. We know Newton's laws say that. Einstein says it's very simple. He says the following. Imagine you were on the surface of the Earth, which is like here. And you can forget about all the little arrows. I apologize for that. Imagine you were just on the surface of the Earth and you were at the equator. And you had your friend at another part of the equator. Let's say that you start going toward the North Pole. Both of you will think that at the moment, near the equator, that you're parallel. You're not moving or diverging from each other. You're kind of parallel to each other. But eventually, once you reach the North Pole, well, you've intersected. In so-called Euclidean geometry, parallel lines will never intersect. But when the surface is curved, you intersect. That's all gravity is. Einstein says that gravity is just the curving of space and time, so it's curved. And everything, unless it hits something else, is moving on straight lines, as they think. And it just turns out that the surface is curved and you meet up. That's attraction. That's how things merge and come together under gravity. So it's actually very simple. There's no forces, there's nothing like that. It's just curvature of space and time, and everything follows straight lines in that curved space-time. Okay, what about black holes? So I love this picture when he sticks out his tongue. I don't know why he did that. I guess it was a joke or something. So Einstein's black holes are very neat and very clean and very simple. They have a few things that I want you to know about. One of the things is the so-called ergosphere. Now, ergos comes from a Greek word that means to work. The reason why it's called that, a working sphere, is because outside the black hole, this ergosphere, which is the purple shell around the black hole, it's a place where you can get energy out of it. So this is where I said a black hole is more than just the event horizon. The event horizon is this yellow thing, sort of a sphere. The ergosphere is actually outside that. So it turns out that this is a way, well, it turns out the ergosphere, in some sense, stores all the rotational energy of the black hole. Since it's outside the horizon, you can get it out. So you can actually extract that rotational energy, as I'll talk about in a second. The event horizon is special because nothing can escape once you're inside the event horizon. This is actually how it's defined. And black holes, under all circumstances that we are familiar with, have event horizons. Now, how do we understand the event horizon? How do we understand its undying need to have us inside of it? So the way in which you can understand that is two different ways. One is the following. Imagine a whirlpool where all the water is being sucked down the drain. And imagine you're in a boat. It can only go so fast. The motors can only spin so much. Then if you're far enough away, the whirlpool hasn't sucked you in, you can escape. That's like being outside the event horizon. Now, what if you were on the event horizon? What does that mean? That's like the water flowing in just as fast as your motor can spin. Means you're going to be stationary. You're not going to move anywhere. That's the best you can do. It's like moving at the speed of light right at the event horizon. And that's the only way you can make it stationary, being fixed on the black hole's event horizon, is if you try to boost and move yourself at the speed of light. Now, once you're inside the event horizon, you fall in. And that's because your motorboat can't go any faster. It's going no more fast than the speed of light. Here's another way to think about it that I sort of like. And that is that time flows toward the center. This has to do with Einstein's idea that space and time are not unique. They're not separate. They're the same, sort of. And you can mix them up. What happens inside a black hole is that what was space and time interchange. As you move in, if time was flowing forward, it suddenly begins to tilt. and flow into the black hole. And so that means that eventually it turns out that when you cross the event horizon, time goes only in. So what does that mean? Sounds crazy, right? What it means is that if you want to move forward in time, you can only go in. Space and time are mixed up so much that you have to be forced to move inward because time points in. If you want to move backwards in time, well, maybe you could do it, but nobody knows how to do that. Finally, there's a thing called the singularity. Inside the black hole, there's a singularity, and what's interesting about the singularity is that it's where all the laws of physics break down. But we still have some physics to handle it, kind of. We can kind of probe it with some mathematics. One of the things we do know is that near the singularity, it's not just sort of like this point or this sort of object which is just sitting there quietly. It's actually a very violent place, very chaotic place. And in fact, when you get close, I'll show you a little bit falling into a black hole means. Eventually, once you get close to the singularity, you won't just feel sort of stretching like you may have heard before, so-called spaghettification that we'll talk about in a second. It turns out that you'll be randomly stretched apart. You'll be pulled on your head sideways, and your neck will be pulled apart this way, and then your chest will be pulled apart this way. There's no particular direction. Directions become sort of meaningless. So that means that you'll be ripped apart in all sorts of different ways, like more like a blender than being spaghetti. What's neat about it is you'll actually reach the singularity in a finite amount of time, as I'll talk about in a second. So, death by black hole, part 1. What I want you to know is that a g-force is what we feel when we're sitting on the planet Earth, 1 g-force. It turns out that through experiments that I would prefer not to know about, we know that you die when you reach about 20 g-forces. Now, this is only when it's over an extended period of time. I can slap you in your face and you'll experience about 50 g's, but I won't do it. But if you continuously feel 20 g's on your whole body, you eventually die from cells exploding and all sorts of things. Your eyes pop out, and it's really nasty. So now, what is a black hole going to do to you? Well, here's the idea. It turns out that we're going to start falling into the black hole. When you fall, when you free fall, you don't feel anything, right? That's what we know from Einstein. You just fall, and you no longer are being pushed up by the planet or the star. Well, what you do still feel is something called a tide. Just like the Earth and the water on the Earth has lunar tides and solar tides due to the gravity of the moon. These tides are very simple. They're simply the difference in the